The next thing that we're going to start to talk about after dealing with Coulomb's law and the way that charge is transferred between two objects is going to be the concept of what's known as an electric field. At this point, we haven't really talked about it much, but there's four questions that I'm going to hope to have answered or have you understand by the end of this lesson. The first one being the general question, what is an electric field? Number two, how can I tell how strong an electric field is just from looking at the diagrams that I'm going to have you draw? How can I tell how strong an electric field is? The third thing being, how do I draw an electric field? And lastly, how can I calculate the actual field strength? So these are a little bit more conceptual. This tends to be a little bit more mathematical. And again, these are the four questions I'm hoping to help you answer by the end of this video. So the first thing we have to take a look at is the fact that the electric force is what's known as a field force. And this is something we've discussed in class before, but the main takeaway here is that there is no contact required whatsoever. It's actually kind of unique in the sense that two charges can exert a force on one another and affect the motion of the other without actually touching one another. And it's kind of interesting because the only two forces that we're ever really going to experience that act like that, at least to date, are gravity and electricity. So the gravitational force and the electrical force. Now, obviously, gravity is the attraction of two masses. And at this point, you should know that electricity is just the attraction or repulsion of charges. So while gravity deals with mass, electricity deals with charge. And we'll actually start to see that these two are actually eerily similar when it comes to not only the concepts, but a lot of the mathematics as well. And field forces are always kind of interesting because we don't fully understand why these field forces exist, but we've come up with this concept of fields, electric fields, gravitational fields, as our best way to kind of explain how these are interacting. So again, we don't completely know why, but we have done enough research as scientists to determine how they're going to interact. We can make predictions, we can make calculations, but at the end of the day, especially with gravity, there's still some unanswered questions as to how field forces actually exist. So what I'd like to do is I'd like to start off by looking at gravity and specifically the Earth. And the concept of field forces, I think, tends to become a little bit easier if you start to think about it in this way. If we take a look at the Earth, if I were to place a mass right here and I were to let it go, I think most people would realize that it will begin to accelerate towards the Earth. So there will be a force from the Earth that acts on the mass and pulls it down. Now, granted, the mass will also exert a force on the Earth, but that's very small due to Earth's mass, so I'm going to ignore that. If, however, I placed a mass over here, again, hopefully most of you realize, I take that back, all of you should realize that the force on that mass will act again towards the center of the Earth. If I place a mass over here, or over here, or over here, wherever I place these masses, so long as they're close enough that the Earth can exert a large enough gravitational force, you start to see that all of these lines of force really point towards the center of the Earth. So it's not a far stretch to say if a force field or the field lines are showing me the force at any given point, in this case on a mass, hopefully you can see that if I just draw a general gravitational field around the Earth that looks like this, you can start to see how we use what we call field lines to represent the force, in this case around the Earth. Now all this means is if I were to take a mass and place it here, the force that would act on it would be down. If I put a mass here, it would act towards the center of the Earth. If I placed a mass here, it would again act towards the center. If I place the mass maybe here, it will still act towards the center. So all these lines are showing you are the direction of the force, in this case on a mass, anywhere within this field. So these lines just represent the force, the direction, and magnitude of the force that in this case acts on a mass at any given location around the Earth or around another mass. So that's all that's all a field actually shows you, the direction of the force that in this case will act on a mass. Now there's two things to take a look at. This is on a grand scale. This would be between two different masses separated by a particular distance. You'll notice that as these field lines get further out, the space between them actually gets further apart. If you start to think a little bit, masses that are closer to the Earth will experience a much greater gravitational force. Think about astronauts that are maybe up on the International Space Station. They tend to have less weight, and you can see that as the lines get further apart, the weight or the force of gravity that someone would experience gets less. So you should maybe hopefully make the connection that the further apart these lines get, the weaker the force. So far, two things we should take a look at. These lines simply represent the force that would act on, in this case, a mass surrounding the Earth or surrounding another mass. And the spacing between lines will also show us the intensity or how strong this field is. If I take a look right at the surface of the Earth, the space is fairly small. But if I get further away, I get a much larger distance, and that larger distance means a weaker force at that location. So as I move away from Earth, the lines get further, so therefore I get a weaker gravitational force. If I take a look, though, at a very small section of the Earth, let's say our classroom, it's important to realize that we have something a little bit different. So if we just take a look at our classroom, for example, in the grand scheme of the Earth, this is so small that while we do have a field in the classroom, it should be easy to see that if I have a mass here and I were to drop it in the classroom, it's going to travel straight down towards the floor. If I were to place a mass over here and I were to let go of that, it would also have a force exerted on it down towards the floor. So you should hopefully be able to see that the gravitational force field in the classroom tends to be straight lines that are evenly spaced from one another, and this is what we would call a uniform field. So there's two ways we can look at this. We have a uniform field where everything generally seems to be evenly spaced, and then we have, on the much grander scale, the actual gravitational field that surrounds an object. So while this technically is a part of this, it's such a small section that the space difference between here and here, while it does technically exist, is so small we would never possibly notice it. So it is accurate to say that the gravitational force of weight that acts on your feet is actually stronger than what acts on your head. It's just so small, the difference is so negligible, you never notice it. Even if you calculate it, it's of no significance. But technically, since your feet are closer to the floor, where these will technically be closer together, you do have more force acting on your feet than you do technically on your head. So this is the whole concept of a mass in space versus a uniform gravitational field. And there's a specific reason why I have you look at this example. Now, if I'd like to apply this to electrical charges, well, we can do the same thing. Hopefully you realize I'm not going to place masses around these because electrical charges, they don't attract or repel masses. They attract or repel other charges. Now, immediately I run into a problem. My problem is, when I was dealing with gravity, I only had one thing I could place there, a mass. I would place a mass at any location, and I could determine the direction of that field, because that would be the direction of force on the mass that I placed near the Earth in this case. Hopefully, if you can kind of figure this out, the problem I have here is what charge do I actually place there? Because if I place a positive charge, it will be attracted to this negative, but it'll be repelled by this positive. If I place a negative, it'll be repelled by the negative, and it'll be attracted to the positive. So the problem here is when we're dealing with mass, you just have mass. It's just the one type, mass. When I have charge, I have two different types. So physicists thought over this problem a little bit, and they came up with the concept of what we call the positive test charge. And all that is we assume that you have, imagine if you will, a pair of tweezers, and you manage to pluck one proton, right? And you can place it at the end of some kind of measurement rod. So I have a proton at the very tip of this. If I place it anywhere near a charge, that is how I test the field at any given location. So it's just a kind of conceptual thing we need to accept. Positive test charge, a small charge that's so small it's not really going to influence the field itself. Think of maybe like one proton, and we can place that near any of these objects, and that's how we're going to test this field. So to do a positive test charge, I'm going to assume it's a small little black dot. So if I place a positive test charge right there, positive test charge, hopefully you notice, will be attracted to that negative charge. If I placed it here, the force on that positive test charge would pull it towards that negative charge. Again, if I placed it here, here, or anywhere for that matter, you'll notice that a positive charge will always be attracted to a negative charge. Again, much like the analogy to the Earth and a mass, you should hopefully be able to see that no matter where I place a positive test charge, it will always be pulled or attracted to this negative charge. Therefore, if I wanted to draw the electric field around a negative charge, I would draw a bunch of lines that are pointed towards the charge, fairly evenly spaced around it, and hopefully you can start to see that if I were to place a positive test charge here, it would travel down towards the negative charge. If I placed it here, it would travel down. If I place it here, it would travel up and to the right. In any one of these cases, it's always going to travel towards that negative charge. And that's all these field lines represent. They represent the force on a positive test charge at any location around this field. Similarly, if I take a look at a positive charge, well, if I put a positive test charge here, two positives will repel, so that will be pushed in this direction. If I place a positive test charge here, it will also be repelled. Hopefully you're seeing that no matter where I place one of these test charges, they will be repelled because a positive test charge will be repelled by a positively charged object, and it shouldn't be too great of a stretch to realize that the electric field, which again just represents the electrical force exerted on a positive test charge, is always going to travel away from a positive charge. So for a single isolated positive charge, the electric field will always point away. Well, why? Because any positive test charge placed in this field will be pushed away. A negative charge will always have field lines that travel towards it because anytime I take a positive test charge and place it near a negative charge, it will be drawn towards it. So positive test charge field lines will always travel away. Negative charge will always have field lines that travel towards or arrive at, so to say, that charge. Now that we've had a little bit of discussion there, I just want to give you the general rules for electric fields. So I've included two examples. The gravitational field around Earth, so please realize this is not an electrical field, but I do like the analogies. And I've included just a negative charge. A positive charge would certainly work as well, but I like the analogy between a negative charge and the Earth. It tends to be more concrete for most students. So the first one, as I mentioned several times, the field lines themselves, again on this diagram because it's an electrical field, it represents the force at a particular location on a positive test charge. So no matter where I placed a positive test charge around this negative charge, it will always be pulled down towards the negative charge because a positive and a negative will attract. So these field lines themselves, they just show you the direction and the magnitude of force at a particular location on a positive test charge. As I just mentioned prior to this page, field lines always leave a positive charge. So I don't have one here, but if I drew a positive charge, because I test field lines with a positive test charge, it's always going to repel. So the field around a positive test charge will always travel away because a positive charge will always repel a positive test charge. Field lines always arrive at or point towards a negative charge. And again, that's because a positive test charge at any one of these locations, and even the space in between, will be pulled towards a negative charge. The last thing, I did mention this briefly, but field line spacing represents the field strength at that location. So as you can see, on the surface of the Earth, you are heavier than if you were further away. And at the surface of the Earth, these field lines are closer together. So the space between them is closer than when you travel further away. So you have stronger gravitational force closer to the surface of the Earth. And you have a stronger electric force closer to the charge because these lines are closer together. As I get further away, these lines become farther apart, and I therefore get a weaker force. If I were to really extend these out into a distance, you'll really start to see how far apart they actually start to get. And you can start to see a little bit more how much weaker the force is out here versus in here when they were very, very close together. So these are four important rules. We're going to come back and talk about them a lot. So please make sure you have them in your notes. Please make sure you understand generally what they're stating. And everything that comes after this shouldn't be incredibly difficult. So the last thing I'd like to be able to do, the last two things, are drawing electric fields and actually calculating the field strength themselves. These two should not be incredibly difficult. It's a positive charge. We're going to use a positive test charge. If I place it here, it will travel near. If I place it over here, it will travel towards. No matter where I place this charge, you'll immediately realize that I made a terrible mistake because I was not paying attention. So I'm going to give everyone about 4 seconds to think about this. Make whatever jokes you like. What I should have done, if this is a positive charge and I have a positive test charge, these are all wrong. You should not be pointing towards. These should always go away. Please do not make the mistake that I just made. Positive test charge will always be repelled, so these should always travel away. If I put a positive test charge anywhere near this negative charge, it will always be drawn towards that negative charge. Since a positive test charge will be attracted to a negative, all of these field lines should travel towards. Now these 3 specific cases are known as dipoles because I have 2 charges. And this gets a little bit trickier, but you just have to keep thinking, what would a positive test charge do? I'm going to represent a few positive test charges in each of these cases. We'll take a look at what's going to happen at each of these locations. Now I could draw a whole bunch wherever I'd like, and I may add some after this. But what I'm going to do is I'm going to use green to represent the forces exerted by these. So at this point, if I put a positive test charge, it will be fairly heavily repelled by this charge, but it will also be repelled by this charge, but not nearly as much because it's further away. Same thing, a positive test charge at this location will be repelled fairly significantly because it's very close to this charge, and it will also be repelled generally in a straight line from this charge, but not as much because it's further away. Same thing, over here, this charge repels a positive test charge greatly. This one will repel, but not nearly as much. Here, this charge will repel a positive test charge. Same thing here, but not nearly as much. If we look at these 2 forces, you realize that's a vector. So what I should wind up getting is I will get a force that's between these 2. It'll be a little closer to this one because that one's so much more powerful. So I would get a force like that. Here I would get a force like that, and so on and so forth. The red just represents the net force between these 2. If I were to place a whole bunch of test charges in between, such as, let's say, maybe here, or here, or here, I'll place a few more. You can do the same thing for any one of these points, and you'll start to see that this is repelled fairly greatly by this one, not nearly as much by this one, fairly greatly, not nearly as much. And if, again, I draw the net force, you'll see that it goes in this direction. All right, well, you'll actually start to see, if I were to do these all over the place, you'll actually start to see that this line will travel out, and then it'll curve up a little bit, and this one will go out and curve down. And what's happening is it's being repelled. The force on any charge you place here will be repelled by this one, but it'll also start to be repelled by this one and curve away. Similarly, this will be repelled away, but after a certain point, it will be influenced by this one, so it'll curve away, and similar things will happen here. If I place a positive test charge here, it will begin to be repelled straight up, but this one will have an influence, so it will be pushed backwards in this direction. Same thing. If I'm down here, it'll start to go straight, mainly due to this charge, but because this one has some kind of influence, it will travel in that direction. And I can kind of continue this process throughout. This one will go straight out because this one pushes it away, as does that one. Over here, same kind of thing. This charge will push up, but it will be repelled backwards, down, and backwards. I can kind of continue this along those lines, and you'll see that any charge is going to be impacted by both of these. Now, a different thing happens with a positive and a negative charge, because this charge is going to be originally repelled by this one, but when it gets far enough away, it's going to be attracted by the negative. Same thing here. It'll be originally mainly repelled by the positive, but as time goes by and it gets closer to the negative, it will be attracted. Anything placed in the middle will be pushed away by the positive and attracted to the negative, and I can kind of follow the same thing. The positive takes over, but as it gets closer, the negative will influence it, and you start to get something that looks like this. These I can just kind of continue in this direction, and these would technically go around and come in on the other side. So you can start to see that at any point, if I were to place a positive test charge at this specific location, it would shoot off this way. If I placed it here, it would shoot off this way. If I placed it here, it would shoot this way. So these lines are just showing the actual force at any given location that would act on a positive test charge. As I get further away from the positive, it has less influence, and as I get closer to the negative, it gains more influence. These two charges have the same, these are the same charges, so you can kind of see what happens here. So I really shouldn't get anything different here. I should get lines that act in much the same way. There should be one major difference that hopefully you guys are starting to see. These are positive charges, so the field lines must point away. These are negative, so the field lines must point towards. Again, these are just showing the direction and magnitude of the force at any given location. So if I were to place a charge here, well, if it's a positive test charge, it's being greatly attracted here because it's very close. Over here, we're getting some attraction, but not nearly as much, so it's something like that. And as you can see, that's exactly why this net force vector kind of travels along here. As I get closer, that charge will be very greatly attracted here. It's even further away, so not nearly as much. So that red net force generally follows where the net force would be. So at any one of these locations, it's being pulled greatly this way. I apologize. Greatly this way, not so much this way, and it's going to travel along. So at any one of these points, again, you can hopefully see that this is just the net force at that location. The last thing you'll need to be able to do is calculate the electric field strength itself. So what we know is that the electric force at any given location is found using Coulomb's law, kQq over distance squared. So all we have to do is say, well, if I want to look at this specific point, I could sit here and place a charge there and find that charge at that location, and then I could place another charge and another charge and another charge and keep calculating different forces. Or what I can realize is that the electric field strength, not the force, but the electric field strength, is really just going to be the force at a given location per the amount of charge that I place there. So rather than keep taking actual charges and placing them there, I could say, well, I know this charge. I want to know at that location how much force will I get per coulomb of charge that I place there. So electric field strength, which we represent with the letter E, is really just going to be equal to the force per unit of charge. So what this will tell me is at this location, that field strength, I'll get a certain amount of newtons, so the units on this, a certain amount of newtons per coulomb of charge that I place there. So rather than saying if I have a 1 coulomb charge, what's the force? If I have a 2 coulomb charge, what's the force? You're really saying at this specific point, for every coulomb of charge that I put at that location, how much force will I get? And that would be found using your electric field strength equation. Now, if I know that E equals F over Q, and I know that F equals KQQ over D, I should also be able to say that E equals, I'll replace F with K, QQ over D squared, and if I'm dividing that whole thing by Q, one of those Q's will cancel out. So a second way to rewrite this same equation would be your electric field strength is equal to Coulomb's constant times Q divided by distance squared. And an important thing to realize here is that this Q is the actual charge causing the field. It's not this charge over here, it's the actual charge that's going to create that field around it. So we know that this positive test charge has a field. That field is a product of its charge, of its strength. So these are two equations we can use in order to try and calculate the field strength. You'll have some examples to go over with this, but just to show you a quick one. Let's say here I have a positive 2 microcoulomb charge. These are not charges, these are just points in space. I'd like to know what is the electric field strength at A, what is the electric field strength at B, if A is 10 centimeters away and B is 4 centimeters. So if we take a look, if I want to look at A first, again, I don't need two charges because I'm only concerned with the electric field due to this charge. So I will go ahead and say if I want the electric field strength at A, I'm going to need K, which is Coulomb's constant. I'm going to need the charge itself. Sometimes you'll see it written as big Q to represent the source charge, the actual charge causing that electric field, and the distance squared. So we here know that 8.99 times 10 to the 9th is Coulomb's constant. In this case, the charge that's causing the electric field is 2 microcoulombs. And I'm going to divide that by my distance squared. We don't like centimeters, we like meters. So 0.1 meters. So that should be 0.1, and I have to square it. So if you give me a second, so I can grab my calculator. What we can do is we can take Coulomb's constant, which is 8.99 times 10 to the 9th. Again, multiply it by 2 times 10 to the negative 6th. And I can divide that by 0.1 squared. And if I did that properly, which I did not, divided by 0.1 squared, what I get is I get 1.798 times 10 to the 6th. And remember, this is, even though it's all this, it's the same as force per charge, so it's newtons per coulomb. Now, the reason this number is so large is because the coulomb is a very large unit of force. For every coulomb that I place at location A, I will get this much force. If I place 1 coulomb at location A, I get 1.798 times 10 to the 6th newtons, roughly 1.8 million newtons of force. Again, a coulomb is very large. That's like saying I'm placing a lightning bolt there, which I obviously wouldn't do. If I place 2 coulombs of charge there, I get 2 times this number. If I place 5 coulombs of charge at that location, I get 5 times that number. And that's why this electric field strength is such a powerful value. Rather than finding specific force on a specific charge, it allows me to find the amount of force that I get per coulomb of charge that I place at that location. So if I want to do the same thing for B, I would say the electric field strength at B is equal to Coulomb's constant times the source charge, which is 2 times 10 to the negative 6, or 2 microcoulombs. The distance, however, now is 0.04, because we don't like centimeters, and I have to square that value. So if I plug that in, 8.99 times 10 to the 9th times 2 times 10 to the negative 6th, all over 0.04 squared. That should give me k times 2 times 10 to the negative 6 squared. That should give me 1.12 times 10 to the 7th newtons per coulomb, which you'll notice is a magnitude of 10 larger than my previous answer, and that's because I'm over 2 times as close. So if I'm closer, I should get more of a force because those field lines are much closer together and I have a much stronger field. This is a general example. The main takeaway I'd like you to realize is that these are not charges themselves. These are points in space, and by doing this calculation, it allows me to figure out that at that location, I will get this many newtons of force per coulomb of charge that I place there, and at location B, I get this many newtons of force per coulomb of charge that I place there. So I hope this wasn't too much all at once, but again, at this point, you should be able to tell me what an electric field is. It's just the force that will act on a positive test charge at any location. You should be able to tell me that the strength of an electric field is related to the spacing between those lines. We draw electric fields by essentially using a positive test charge and denoting the direction of the force at any given location. And I can calculate the field strength of any charge using my electric field strength equation. Either E is equal to the force over the charge, or the electric field strength is equal to Coulomb's constant times that source charge over the distance from that charge squared. So 4 basic questions. I hope this was helpful.